Another fun integral, which actually has some practical use. So if you want the challenge, pause the video and see if you can calculate that integral without any hints. Otherwise, after the break, I will give you a small hint to simplify the calculation of this integral. Okay, here comes the hint. The hint is to use the following recurrence relationship, namely hn plus 1 of x. So hn plus 1 of x. We know that this is equal to 2x hn of x minus 2n hn minus 1 of x. And then looking at the integrand over here, we have xhn squared, and the idea is to get that information from that equation over here. So with this particular hint, pause the video and see how far you can get. Okay, let's go. Our integral is an integral from minus infinity to plus infinity exponential minus x squared. And then we have the square of the stuff here. So this guy moves to that side, and then we divide by 1 over 2. So after the square, it becomes 1 over 4. And then we have the square of hn plus 1x plus 2n hn minus 1 of x squared. dx, of course. Okay. In order to simplify our notational load a little bit, let's go back to the definition of scalar products between Hermite polynomials of different orders. So if we use this notation, then we can write our scalar product as the integral from minus infinity to plus infinity of our weighting function, exponential minus x squared, hi of x, hj of x dx. And this will allow us to expand this using a much more compact notation. So if we do that, we see that our integral becomes, and then first we have the square of this guy over here. So this is going to give us 1/4 the scalar product of hn plus 1 with itself. Cool. And then we have, again, 1 over 4. And then we have the double product going on here. So this is going to give us 4n, a scalar product hn plus 1, hn minus 1. And then lastly, we have 1 over 4, 4n squared scalar product of hn minus 1 with hn minus 1. Now, the good news of writing this as scalar products is that we also know that the scalar product between different orders of Hermite polynomials is 0. So we've also derived that. So we can now make use of that to annihilate that second term over here. And we also know that if we have the scalar product of a Hermite polynomial by itself, that's basically going to give us the normalization according to that definition of scalar product. We have also calculated that for a Hermite polynomial of order n, that's 2 to the power of n factorial square root of pi. So pause the video, take the final steps, substitute this thing in here, and simplify the result as much as possible. Let's go. So the first term is going to give us 1 over 4, and then the normalization integral for the Hermite polynomial of order n plus 1. So that's 2 to the power of n plus 1 factorial square root of pi. And then the next term is going to give us n squared times the normalization for n minus 1. So this is 2 to the power of n minus 1 factorial, and then also the square root of pi. The good news is if we combine these two terms here, these two factors rather, we have exactly this thing over here. So 2 to the power of n minus 1. So we can factor that one out. So 2 to the power n minus 1. Let's also factor out the square root of pi. And then we have n plus 1 factorial plus n squared n minus 1 factorial. We're almost there, just working a little bit on this thing here. So let's bring in some more n factorials. So 2 to the power of n minus 1 square root of pi. Now n plus 1 factorial is obviously n plus 1 times n factorial. And then we're also going to split off one factor n here to combine with n minus 1 factorial to give us n factorial. So we have n times n factorial. So now we can bring out the n factorial again. So we have 2n minus 1 square root of pi n factorial. And then what we have is n plus 1 plus n. So the end result is 2n plus 1, 2 to the power of n minus 1 square root of pi n factorial. Okay, and that's the satisfying result of our calculation here.